Hello and welcome back to Calculus 1 section 2.3 on computing limits. So now we're going to take a look at a number of different ways, techniques to compute limits. We did talk in looking at the graph, right? We saw that one when we said, oh, it goes to positive infinity, negative infinity, goes to zero or something. So graphs. Let's say number one, graphs. Number two, chart. Right? And those two were both in 2.2. Number three, and the first thing we're going to cover now, is plug-in. We'll talk about that. Number four, algebra. Number five, well, we'll see there are also ways to compute this using some other theorems in calculus. So we can come in or I can, sandwich theorem. We'll talk about it. So all of these are 2.3, and then there is more coming up later in the chapter in 2.4, 2.5, in terms of asymptotes and infinities and so on. So we'll deal with that when we get there. Let's talk about the plug-in method. That's what we are. So plug-in. This one is dangerous. It's the easiest, it's the cheapest, it's the fastest, right? But then it's dangerous because it doesn't work all the time. Now, what is the method? Well, the method is simply you are plugging in the value in the formula and computing. But you have to be very careful that you are not ending up with one of those situations when the limit does not exist. So if you have the limit x goes to 3 of x squared, you can compute it because we saw that the pre-calculus and the limit give you both 9. If you have limit x goes to pi over 4 of sine x, well, you know that sine x has no issues of any kind in terms of interruptions, 0 in denominator and all that kind of stuff. So simply sine of pi over 4 is root 2 over 2, and you are good to go. So if you are able to plug in a value and get a number without any issues, then you can use. Now here, I'm going to write this in blood. Plug-in method fails when we have 0 in denominator now. It's not the only time when it fails, but most of the time in problems you have 0 in denominator and plug-in method is not good anymore. So if you have the limit as x approaches 0 for 1 over x, well, cannot use plug-in method. Cannot use plug-in method. So it's important to know the situation when you cannot use it. It's so nice, it's so fast, it's so simple, right? Because you have been doing this, plug in the number into the function and get the y value. You have been doing this all the time. So you might want to solve every limit problem that way, but you can't. So here is the 1 over x problem that cannot be solved. And the next scary part, which is what damages most of the grades, obviously, is when you say, oh, 0 in denominator limit does not exist. Hell no. We'll see the examples as well, where you have 0 in denominator and the limit is a number of some sort. So you have to be very careful with the 0 in denominator. We are going to deal with algebra and other methods, right? But now on, the plug-in method It's just you plug in the value in the formula, and if you have no 0 in denominator, nothing weird is happening, you are done. The problem is solved. So another example here, let's say limit as x approaches to ln 4 of e to the negative x, let's say. Let's say this is your problem. Well, e to the x is not going to give you, you can rewrite this as limit x goes to ln 4 of 1 over e to the x. And you know that e to the x cannot be 0. That's the pre-calculus, right? When you graph e to the x, it never cuts through x-axis. So y value is never 0 for e to the x, so e to the x can never be 0. So you don't have the issue of this being 0 in denominator ever, so you are allowed to plug in. And when you plug in, you get 1 over e to the ln 4, and then ln and e will cancel, and you just get 1/4. So it's a very simple calculation for this particular problem. But other problems where you have 0 in denominator, well, you can't do this. Now let's go and take a look at the algebra approach to solving this problem. And the first candidate for our limit is going to be, let's say, limit x goes to 3 of x squared minus 9 over x minus 3. So we are looking at this particular limit here, and clearly you are drawn, I know, right? You are drawn to the idea to plug 3 in and be done, so you can do other things in life, right? So you plug 3 in and you get 9 minus 9 divided by 3 minus 3, and you get 0 over 0. So plug-in method, I'll write it in blood. Plug-in method does not work because 3 minus 3 equals 0 in denominator. You also have the 0 in the numerator, so it's technically 0 divided by 0. But still, so how much is 0 divided by 0? Right? How much is 0 divided by 0? Are you thinking about it? Because this is technically what it is. Does it look like 0 divided by 0? Sure, right? 9 minus 9 is 0, 3 minus 3 is 0, 0 divided by 0. How much is that? Let's see. So in this case, you are supposed to use algebra to try and change this in some way, or get rid of this denominator that is preventing you from plugging the value into compute. Any suggestions? Yes? That will be when the square roots are around and stuff like that. Factoring, yes. So we have x minus 3, x plus 3 in the numerator, and we have the x minus 3 in the denominator, and those two cancel. So now we have the limit x goes to 3 of x plus 3. And now it's 6. Looks like 0 divided by 0 is 6. Didn't know that, huh? Well, now you learned. So this is the way to work the limits out when you have 0 in denominator. You have to figure out the method or the way, whether it's factoring, canceling, rationalizing, adding fractions. There are a whole bunch of things to do just to get rid of the 0 in denominator. And when you get rid of the 0 in the denominator, you will be able to plug the values in, just like I plugged 3 in here and said 3 plus 3 is 6, and I'm done. Right? Now, if you don't have this last line, what kind of conclusion can you draw from the upper line with 0 divided by 0? And the answer is, you can't draw any conclusions, right? You can't draw any conclusions. So you have to be careful with computing these things. Let's take a look at another example. Say we flip this. Let's say I have the limit x minus 5 divided by x squared minus 25 as x goes to negative 5. Can I plug in? No. Negative 5 squared is 25. 25 minus 25 is 0 in denominator. So, cannot plug in. Cannot plug in because we get 0 in denominator. Okay. We know what to do. We can factor. So now when you factor, you get limit x goes to negative 5, and you have your x minus 5, and now you have your x minus 5, x plus 5. These cancel, and you get now the limit of x minus x goes to negative 5 of 1 over x plus 5. Can I plug in now? It's still 0. So here we go. Sad face. Still cannot plug in. Holy nightmare, this problem is evil. Right? Now, is there any other algebra that you can do? No. There is no more factoring. There are no roots to rationalize. This is the end of the road. And when you hit the end of the road, you get to graph the function and take a look what's happening. Now, to graph 1 over x plus 5, you need to know basic pre-calculus, shifting left, right, up, down, reflecting, and all of that stuff. So now, since we can't use any more algebra because there's nothing else algebraically that we can do here, that's the simplest form, we now have to go and graph. So now, need to graph this. There we go. So what we know is that y equals 1 over x looks like this. Right, that's what we know. We also know that 1 over x plus 5, this one is what? Shift to the 4 of you said right, and then we finally have left. Shift to the left 5 units. Shift to the left 5 units. Once you shift to the left 5 units, you actually get to see the graph. You are going to make a vertical asymptote at negative 5, and you will draw the same 1 over x shape that you are all used to. Now, since you are looking at the overall limit, you have to look at the Romeo and Juliet approach. So, left is going to give you negative infinity, right is going to give you positive infinity, and finally you can claim that limit does not exist in this case because the limits did not agree to go the same way. So in this example, we had to go through some extra hoops. Previous example, we just canceled and it was enough. We were able to plug the value in and we're done. In this example, no. We had to work harder, and since we had this situation where you can't proceed anymore with algebra, we had to go back to the primitive ways, which is graphs and charts, whatever makes you happy. Graphs are much faster if you know how to graph. If you don't know how to graph, then you will be picking values, working out the chart to figure things out. So in this case, right, limit does not exist. And if I am to swap the two, put the x squared terms up and the x minus 5 in denominator, it will be a completely different problem and a completely different scenario and a different answer. And we would have less work to do. So that's a cool problem. What else? So let's take a look at the limit of difference quotient. We talked about difference quotient last class. So let's take a look at the limit of age goes to 0 of 1 over x plus age minus 1 over x, everything divided by age. Now, if you are screaming in your head, why? You'll have to hold on sometime. Trying to corner the rage. Can we plug in age equals 0 and be done? No, because it's divided by age. So now we have to massage this with algebra to get rid of that age in denominator. And then when that is done, we can finally solve the limit by plugging in the value. So what is the only thing that you see you can do immediately? Yeah?
Get rid of the denominator?
Like this?
No.
No.
Going to multiply the top age at the bottom age.
Well, you're just going to create an age squared, and if you create age squared, then still 0. And if you divide by age to kill it on top and the bottom, then the bottom will cancel. The top will have, both of those fractions will have age in denominator. You can factor the age out and still 0 in denominator. Yes?
If you flip it.
Or we only have one side of the equation. What you are referring to is the proportion A over B equals C over D. If you flip one side to B over A, the other one flips on D over C, but I do not have the other side to do that, so I can't flip. Any other suggestions? Yes?
Find the common denominator.
Yes, add fractions. I did mention that one of the methods in algebra, I said factoring, I said canceling, I said rationalizing, and I said add or subtract fractions. Right? So in this case, you are going to add these two fractions. Well, subtract, same thing. So we are going to subtract these two fractions. We need common denominator. So the first fraction will be multiplied by x over x, and the second one by x plus age and x plus age. So we have limit, age goes to 0, and now I have x divided, hold on, the main division line, and then h on the bottom. There we go. So we have the common denominator now of x plus h times x, right? That's the common denominator. And on top, I have x minus h. Because when I have that negative 1 times x plus h, negative 1 times x is negative x, and negative 1 times h is negative h. So those are the values. So now we go the limit, h goes to 0, and these two x's drop. So what I have is negative h divided by, you can put x in front, so x plus h, and then h, and I'm going to put over 1. It's easier to deal with the double fraction when you have fraction divided by fraction. Number of ways to deal with a double fraction. This is technically a over b over c over d. That is equal to a over b times d over c. So you can see that it's ad multiplied, and those are the two that are far apart. So we get limit h goes to the 0. Multiply two that are far apart, you get negative h. Multiply two that are close by, which is b and c, you get x times h times x plus h when you multiply those. And that's what kills h, as you can see. H is gone because you have h in the numerator, h in the denominator. So now we are looking at the limit h goes to 0 of negative 1 divided by x times x plus h. And at this point, it's okay to plug in h equals 0 because you get x plus 0, and that's just x. So the whole thing is negative 1 over x squared, because h over here goes to 0 because h goes to 0. So you have x times x only. Now, this problem is interesting because you have two different variables in it. You have x variable and h variable. See, limit only impacts the variable that is mentioned in the limit, which is h. And x is not bothered at all. So this is limit as h goes to 0, which is why you are killing h. And then you have x times x left, which is x squared. So it, x value prevails all the way to the end of the problem. So you have to be careful which variable limit affects. It's not going to affect all of the variables the same because it depends where they are in a problem. You should put a star next to this problem. 2 stars, 3 stars. Put 3 stars next to this problem. 3 stars is a good amount. If the maximum amount of stars you can have is 4, then 3 would be a good number for this one. This is something very important in calculus, and it's coming up. In chapter 2, we just learned to go through calculations, meaning and definitions and stuff regarding this calculation, which will be repeated many times in homework in all possible shapes and forms, and exams and stuff like that is for later in calculus. So that's why I'm asking you to start this problem. It's important. So that was the limit of the difference quotient, and we had to deal with the 0 in the denominator. Yes?
I have a question. What happens to the h over 1?
They multiplied. The two that are far apart multiply on top, and two that are close by multiply on the bottom. The way you deal with the double fraction.
I thought that was like that becoming that.
You did a reciprocal, right?
Mm-hmm.
Yeah.
You can just say, okay, 1 over h. Flip that one up, and that's it. There are many ways in which you can solve this. Depends whose algebra class you went to. Because different people teach it differently. We just need to know that from here you get there. Now.
Wait, so why were you able to flip it there but not in the beginning?
What do you mean flip it there but not in the beginning?
Find the reciprocal of the initial equation, like 1 over x plus h minus 1 over x over h. Why couldn't you find the reciprocal there?
But these are the two separate, they're separate terms. They're two terms. I had to combine them first, and then I can deal with the. Can I multiply by 1 over h immediately? Yeah, but I'll still have to add it later.
Okay.
So either way, this is more mainstream way to do it. But one thing you cannot do is to put h on top and put this on the bottom. That's one thing you cannot do. To just flip the fraction. Okay, what else is cool for this? Well, let's. We had plenty of examples. Let's do another one of these. But I'm going to say compute limit as h goes to 0 of f of x plus h minus f of x divided by h for f of x equals x squared plus 4, let's say. So you are given the function. The formula for difference quotient you should know from pre-calc 1, but we'll have to give you more time, right, to get there. So first compile the difference quotient, then put the limit in front of it, and then compute. Let's see. 18 seconds left. Okay, let's take a look at this problem together. I already have f of x, which is the piece that goes there. The only one I need to compile is this part and then plug everything in. So f of x plus h is x plus h squared plus 4. So these two have to be the same, where you replace every x by x plus h. Now you expand this, you get x squared plus 2xh plus h squared plus 4. And now we plug everything in. So limit h goes to 0 of x squared plus 2xh plus h squared plus 4 minus x squared minus 4, when that minus distributes, divided by h. Remember, this minus will distribute to both of these terms, which is why we get the negative 4 over here. Now, the negative x squared kills x squared, negative 4 kills 4, and we have the limit h goes to 0 of, factor out h, you have 2x plus h. Divided by h you want to get rid of. Well, now you can. So kill it. And you have the limit h goes to 0 of 2x plus h. Now your h goes to 0. And the answer is just 2x. So this is one of the standard exam problems, I would say. Exam 1. Whole bunch of homework with these difference quotient calculations in 2.3, because this is going to give us something extremely important later on, and these calculations need to be known. So the function is given, you have to create f of x plus h, and then plug everything in. So you have f of x plus h minus f of x over there, and then the whole bunch of stuff will cancel. And you go from there. Okay. So now we have one more technique to explore in this section. So we had the plug-in method. That was the first one. I just need to get to examples because not every example can fit here. So first one was plug-in method, and we said that method fails immediately when you have 0 in denominator. So if you are able to come up with the answer of whatever finite number when you plug in the limit value into the limit, you are done. That's it. But if you can't, then you have to use some kind of algebra to come up with either cancellation, adding fractions, there's factoring, there's rationalizing, whole bunch of stuff. I'm logging in and freak out every time because sometimes they ask you to solve those little puzzles, you know, when they, yeah, just like click all the images with cars or storefronts or something. You know that stuff, right? So stressful because they, you know it's a car. You can see 2 pixels of it. Do you click it? Because if you don't click it and you're supposed to click it, then you have to do another one after that. And that is just devastating.
You don't have to click all of them. You only need to click 3.
Yeah.
So if it says a car, and the car is in like 5 pixels, you only need to click 3 pixels. Like it's in
Wow.
5 boxes, you only need to click 3 boxes.
Really?
Yeah.
How do you know that? I never heard that. No one ever told me that. You just made my life. Thank you. It works for storefronts as well, right?
It works for all of them.
And the crossing, okay. Because you just need one letter in the login for anything, and immediately it pops up. It's like, come on. Then the voices in the head start. Do it. It's terrible. Anyway. So one more method, then we're going to take a look at the properties of limits, and 2.3 is over. We're going to take another break. The next 2 sections are very short. Obviously, we're not going to have time for a whole bunch of stuff today, but we'll get what we can. So the next one is the sandwich theorem, also known as the squeeze theorem, depending on which book you read. So this theorem is interesting because it allows you to solve limits in some really crazy situations. See, if you have, let's say, trig involved. Trig is periodic and it tends to oscillate, and limits don't like that because the limit likes to know what the value is by observing the values that nicely and calmly go to the value which is the answer, like those. Now smoothly we went into that 9, right, looking at the values. But when you have a trig function is going to go over here, and then it's going to do, let's say, like that. Really? Right? So you can't make the smooth guess looking at the chart of values, because you're going to have a positive value followed by the negative value followed by the positive value. It is just, too much in that case. So the squeeze theorem, sandwich theorem, is helpful when you have situations like this. Now this graph belongs to a very interesting function. So you say limit x approaches 0 of x squared times sine of 1 over x. Right? So now you go and say, okay, can I plug in? Right? If you can plug in, it will be great. But you can't, because you have sine of 1 over x, and there's your 0 in denominator, right? So it will be sine 1 over 0. And that's no bueno. So we can't plug in. So what is this theorem about? Well, this theorem is about figuring out 2 functions that are going to squeeze or sandwich in the function that you care about. So if I have a function on top that goes like this, and a function on the bottom, let's say, that goes like that, you see that the function, the black function, is sandwiched in between the red and the blue. It's literally a piece of bread, cheese in the middle, right? If you're lactose intolerant, 2 slices of cheese in the middle, and then a piece of bread on top, right? And then you take a look. See, you are going to find a function that is going to have the same limit at the point here. And if something is squeezed in between, well, has to have the same value. So we can construct that easy. What we know from pre-calculus, from trigonometry, is that sine of any function has to be bounded by 1. Meaning, all of the answers, the values that sine or cosine give out have to be between -1 and 1. So this tells us that -1 is less equal than sine 1 over x less equal than 1. And then when you compare this with this, you see that x squared is missing. So you multiply this 3-sided inequality by x squared everywhere, all 3 sides. And from there, you get negative x squared is less than equal than x squared sine 1 over x less than equal than x squared. Oh, this is really cool. Because now, if you take a look at the limit of negative x squared as x goes to 0, you are going to get 0. And when you take a look at the limit of x squared as x goes to 0, you're also going to get a 0. So what's going to happen with something that is squeezed in between? It has to be 0. Because the only value that you can squeeze between 0 is another 0. You can put 10, right? So these two together will tell us that the limit of x squared sine 1 over x, which is trapped in between, also must be 0 because the squeeze theorem said so. So depending on which book you guys read and observe, you will have the name either called as sandwich theorem or as the squeeze theorem. Either way, that's what it is. Cool? Your homework assignment is probably going to have like 1 or 2 problems. If you're having trouble with this, please look at a book or whatever book, or find more problems online if you're having issues, and then stop by and ask questions. The last thing for 2.3, and then we're going to go for a break, is limit laws. And this is going to be important for later, one section in chapter 4, but this is something that you are going to start 10 times if you are taking Calc 2. Calc 2 has 2 parts. Well, like, there is a third part which is only 3 sections prep for Calc 3, so ignore that. Calc 2 has 2 parts. The second half of Calc 2 is going to be using limits in every single problem. And this is where these limit laws come in. So these limit laws might show up on a first exam, might show up on a final in Calc 1, but you will see these a lot in Calc 2. So you need to know this stuff. And it's good if you learn it now than to learn Calc 1 and Calc 2 when you're taking Calc 2. So, number 1, if you have limit x goes to a of f of x plus g of x, right, so you're adding 2 functions together like this, you can take independent limits of each of the functions and then add the results. So you can solve limit x goes to a for f of x plus limit x goes to a for g of x separately. And then let's say one will give you 7, the other one gives you 13, and then 7 plus 13 is 20. Same rule for subtraction. Limit x goes to a, but I'm just going to start abbreviating this. F minus g is going to be the limit of f minus the limit of g. So x goes to a. If you have a constant multiplying the function, you can kick it out in front of the limit. So if you have the limit of cf of x, you can kick this constant c outside and then just figure out the limit of f of x and then multiply by the number. Number 4 and 5 are only for limits. The rest of the calculus will have much different rules. So limit of f times g separates each one. So you can do limit of f times limit of g. Guys, this does not work later on. It's a very dangerous rule. It works for limits, so sure we have to list it, but it doesn't work anywhere else. So f over g is going to be limit of f, x goes to a, divided by the limit of g, x goes to a, and g is not allowed to be 0, obviously, otherwise it's not good. The last one, exponents. So if you have limit of function to any kind of exponent, now you have to know what flavors you have here. First, you can do the limit of f of x, and then when you are done with that limit, you can apply that exponent. So these are the rules. Now I need to talk briefly about this idea of f of x raised to the nth exponent. This n can be integer. Well, if I split it that way, Alright, it can be integer. And if it's integer, you get polynomials. If n is negative, see, that's why I didn't want to say integer. That's bad. So if n is the whole number. No. N larger than 0, whole number. There we go. N less than 0, whole number. Then you get rational function. And the third one is if n is a fraction. Then you get radical. So this one case covers all of these, and I'm going to immediately give the example. X squared polynomial. X to the negative 2 is actually equal to the 1 over x squared, and that is rational. And x to the 1/2 is square root of x, which is radical. We are going to see this situation in both derivatives and integrals coming up. So when you write x to the n, or x to the a, or x to the whatever, having different types of numbers as the exponent changes completely the type of the function you have. And that's very important to distinguish between these two. And it's the same rule for all of them, actually. So we're not going to learn 3 different rules. You just need to know that all of these types of functions are covered by the same rule. So if you see f to the n, you see x to the n, right? You always have all 3 of these features mushed into the same category. So rational, polynomial, rational, and radical functions. And we are going to have one derivative formula take care of all of them because we just have x to the n. Integration, the same thing, right? Just one formula for x to the n, but it takes care of all of these different types of functions. And that's it. Okay, just a little side note there at the end.
Can you scroll a little bit to the next one?
I can. You're welcome. Any other questions? No question? All right.